The next section, section 1.6, which is the last section in chapter 1, is on continuity. So the idea of continuity is if the general idea of continuity is if you can draw the function without picking up your pen, then it will be continuous. So for example, the function y equals x squared is a parabola, and I can draw that parabola without having to lift my pen up, because every point on that parabola is connected to the point before it, and there are no holes, there are no breaks, there are no asymptotes. It is a continuous function. In fact, all polynomials are continuous functions when you graph them. All rational functions, like the square root of x, are continuous functions. But they are continuous on their domain, because the square root of x in the real number system cannot have a radicand that is negative. So the domain of this is all the numbers from 0 to infinity, and as long as I use those, I don't have to pick my pen up to draw the square root of x. It is a continuous function. The other way to think about continuity is that if a function is going to be continuous at a certain point, like if I let x be the value a, to be continuous at a certain point, the limit as you approach that value of your function has to be equal to the function value at a. And the way that works is we've already looked at the function x squared minus 1 over x minus 1. And we've talked about the fact that that function, because I can factor and divide out the x minus 1's, that function is actually equivalent to the function x plus 1 everywhere but one point. And the one point is when x is 1. When x is 1, the original function does not exist. But this function x plus 1 does. It exists. It's the value 2. So the original function, if I took the limit as x approached 1 of this original function, I can find a limit. I can divide out my x minus 1 factors, and I can direct substitute in and get a limit as x approaches 1 of 2. What that looks like is that this original function looks like the function that has a y-intercept of 1 and a slope of 1, except that I can't fill that dot in, because when the x is 1, the function, the original function, does not exist, and I need an open circle. So this line that I'm going to draw has a hole in it, and that hole is at 1. Because I have to pick my pen up to finish drawing the rest of the line, this function is not continuous at 1. But by the definition, it's not continuous because the limit as you approach 1 is 2, but f of 1 is undefined. So when the limit as I approach 1 of the function does not equal the function value at 1, then this function is not continuous at the value 1. Another way that a function cannot be continuous, besides having a hole in it, is if it has an asymptote. For example, the function 1 over x. That graphs to look something like this, and that asymptote means that I will definitely have to pick up my pen to draw this function. And if I tried to get a limit as x approached 0 of the function, it doesn't exist. And because the limit doesn't exist, it's got to be discontinuous. The limit from the left is negative infinity. The limit from the right is positive infinity. So if you remember from previous class, that's why it doesn't exist. It cannot be continuous with an asymptote. The final way that a limit might not exist is if you have a piecewise function, such as a function where it's 5 minus x between the values of 2 and 3, and then it becomes x squared plus 2 when you get from 3 to, let's say, I'm sorry, I had the wrong limits. From -1 to 2, and from 2 to 3. So this particular function only exists between -1 and we'll include 3. Between -1 and 3. That's its domain. Not all real numbers, but this small portion of the graph. From -1 to 3. And between -1 and 2, it's a line. It's a line with a y-intercept of 5 and a slope of -1. So down 1 over 1, down 1 over 1, and we can go up 1 over 1 if we want, but it's this line between -1 and 2. When you get to 2, we'll have to, not include 2 in the second part. If we included it in the first part, it becomes a parabola, x squared plus 2. If I plug 2 into this value here and I get 4 plus 2, that's a value of 6. Well, that means this parabola starts way up here at a value of 6 on the y-axis. And then it starts going up like a parabola would do with a positive coefficient. So this function that we're talking about that starts here and ends here is definitely not continuous, because I can't draw this line and that parabola without picking up my pen. So when you have a piecewise function, if the two pieces don't fit together, it's not continuous. The limit, as you approach the number 2, which is where the domain breaks, from the left would be found by taking this piece, the 5 minus x piece, and doing direct substitution. The limit as you approach x from the right would be come from taking the other piece, the x squared plus 2 piece. And when you do that, you find that 5 minus 2 is 3, but 2 squared plus 2 is 6. And so if the limit from the left and the limit from the right are different, the limit doesn't exist. And if the limit doesn't exist, it can't equal the function value. And in this case, the function value at 2, you would have to use the piece where 2 is included in the domain, and that would be 3. So in other words, this function is continuous from the right because the limit, continuous from the left because the limit from the left equals the function value. But it's not continuous from the right because I don't match the function value. There's a very quick fix for this. I just need to pull this parabola down. And so the way that you would do that is you would change that piece of the function to be x squared minus 1. If this piece of the function becomes x squared minus 1, then when I plug 2 in, I get 4 minus 1, I get 3, which is that same function value, and then the parabola would look like this. And so it would then become a continuous function, because when this becomes x squared minus 1 and this becomes 3, the limit as I approach 2 will be 3, and it equals the function value, and that's why we're continuous. So a piecewise function can be made continuous if it isn't to start with a little adjustment. And that is continuity, and I'd like you to try your section 1.6 homework.